So they discovered electrons. So then that leads to more questions. So if there's negative charges in the atom, then there's got to be some positive charges. And then how do those things fit together? Are there other particles in there? Are these just like a jumble of little beads or something? Are atoms smaller spheres? Are they solid spheres? Can she learn how to talk? Are they solid spheres? Try saying that 5 times fast. Or is there some sort of internal structure? So at the very beginning, you have to start somewhere. You have to have an initial hypothesis. So Thomson's hypothesis is known as the plum pudding model of the atom. Has anyone here actually had plum pudding? No, we don't have any British students. The closest thing that we might be familiar with would be a blueberry muffin. So this is like the blueberry muffin model of the atom. So in this model, the electrons are like blueberries, and then there's some sphere of positive charge, and that's like the cakey part of the muffin. Okay, and so the blueberries are just like randomly inside the muffin. The electrons are just inside there somewhere. You got to start with some hypothesis. So now we have to introduce one little thing before we can go on. Radioactivity. So we've all heard of this, right? Radioactivity is covered in this chemistry sequence in chapter 20, which comes up in Chem 1B. We have to know a tiny bit here. So radioactivity is the emission of small and energetic particles from the nucleus of an unstable atom. It was discovered at the end of the 19th century by Henri Becquerel and Marie Curie. You've probably heard of her. What's really useful about radioactivity is it allows us to probe the structure of the atom. So atoms are very small. If we're trying to look at what's inside of them, we need something even smaller, right? So 3 types of radiation are alpha and beta particles, and gamma rays. So the one that we're interested in here is an alpha particle. An alpha particle has a positive charge, and of the 3 types, it's the most massive particle. Okay, so all of that to just so I can use the term alpha particles. Okay, so Rutherford. Rutherford was a student of Thomson, and he went along with this blueberry muffin model. And so he did an experiment trying to confirm that. Because you have a hypothesis, that's great, but you got to prove it. You got to show that it might be correct. So he does an experiment where he takes positively charged alpha particles and he shoots them at a very, very thin sheet of gold foil. The plum pudding model would predict that those particles should just go straight through the foil. It's like, if you took a sheet of tissue paper and shot a cannonball at it, what do you expect would happen? Just blast right through the tissue paper, right? Or if you took a volleyball net and shot airsoft pellets at it, they're going to go straight through, right? This was the setup. So here's a source of alpha particles, shooting those at this foil, and then we've got this detector that goes all the way around so that we can see where they end up. This is vastly simplifying the whole idea here. So most of them did go straight through. Some of them got bent a little bit, but some of them bounced back. So you shoot a cannonball at a piece of tissue paper, and it bounces off the tissue paper and hits you in the face. How could that happen? It can't happen, right? So the results were unexpected. Most of the particles went through. That's what they expected to happen. But some particles were deflected and even bounced back, about 1 in 20,000. But Rutherford's comment on this was, it was about as credible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. It was that shocking. So they had to modify or create a new model to explain this. And this is where we came up with the nuclear model. So here we have illustrations of the blueberry muffin model and the nuclear model. In the blueberry muffin model, we've got just this muffin with little blueberries in it, and these alpha particles can just go through that positive sphere. You know, that really was nothing. In this model now, we have something at the center, the nucleus, that is very, very dense. It's really small, but it has a significant mass, incredibly high density. And then the electrons are around this sort of in a cloud. And so when you're passing these alpha particles, shooting the alpha particles at the foil, most of them are going to go through the electron cloud. But if one hits this nucleus, that's like hitting a brick wall. It's going to bounce back. So this led to the nuclear theory of the atom, 3 basic parts. Most of the atom's mass and all of the positive charge is contained in a small core called a nucleus. Most of the volume of the atom is actually empty space in which we have these tiny negatively charged electrons. Now, he didn't even speculate about what are those electrons doing, and we'll talk more about that later in this semester. And then the other idea, very important, there are as many negatively charged electrons outside the nucleus as there are positively charged particles that are called protons inside the nucleus. So an atom is electrically neutral. It has positive and negative charges, but equal numbers of both. So that model was very successful, but it was still not quite right. It was incomplete. And we can show that looking at hydrogen and helium. So hydrogen has 1 proton. Helium has 2 protons. So the electrons are really tiny, so the mass comes from the protons in the nucleus. So if this one has 2 protons, we would expect that helium weighs twice as much as hydrogen, but it weighs 4 times as much. What's up with that? There must be something else in there. So Rutherford and one of his students, James Chadwick, later demonstrated that missing mass, the mass they couldn't account for, was due to neutrons. So neutrons are much like protons. They're about the same size, and they're in the nucleus. But neutrons are neutral. They don't have a charge. Neutrons are neutral, and their mass is extremely similar to that of a proton. So a hydrogen atom has 1 proton and no neutrons. The helium atom, that is 4 times as massive, has 2 protons and 2 neutrons. So for the hydrogen, we've got 1 proton. And for helium, we have 2 protons and 2 neutrons, a total of 4 particles. So helium weighs 4 times as much as the hydrogen. So what are these particles doing in there? We have the nucleus, that's where the protons and the neutrons are, and over 99.9% of the mass. Very tiny. The nucleus is mind-bogglingly dense. So if you were able to take just the nucleus of a bunch of atoms and put them together into a sphere that was as big as a period in your textbook, not very big, it would weigh millions of tons. Most of matter is actually empty space. The electrons are in this cloud, and they are occupying most of the space while contributing very little mass. So the book uses a cloud analogy. So the electrons are like water droplets in a cloud. Let's call it a fog analogy, because we're all familiar with fog here, right? So those little water droplets in the fog are like the electrons. They don't have much mass. They don't actually take up much space, but they're dispersed over a large volume. And so when you try to look through the fog, even though it's mostly just air, those little tiny droplets of water obscure the vision. You can walk right through it, but you can't see through it. Does that make sense? So a cloud, a fog, mostly empty space, it's mostly air. And atoms are also like that. They're mostly empty space. So this bench top seems pretty solid, doesn't it? It's mostly empty space. How does that work? Matter appears solid because the variation in density is too small for our eyes to see. So there's the extremely dense nucleus, and then there's a very not dense electron cloud. But those pieces are so tiny that our eyes can't distinguish them. They're so close together. It's a little bit like looking at scaffolding, or that really looks more like an old-fashioned jungle gym thing to me that we used to climb on. And they put asphalt under here, and people regularly fell off and hit their heads. It's amazing any of us survived. Anyway, we have this big, big structure here. It's mostly empty space. It's got these cross beams and vertical supports, but inside nothing, right? So think about a scaffolding or a jungle gym the size of a football field and 100 stories tall. It's tall. Huge, right? It's mostly empty space, right? But if you get far enough away from it, from a distance, it's going to look solid. Does that make sense? If that was representing an atom, then the nucleus inside of that would be the size of a pea. So we've got this structure as big as a football field, 100 stories tall. That would be a very, very large building, right? And the nucleus, where almost all the mass is, the size of a pea. Mostly empty space in an atom. So what's happening when I knock my knuckles on this bench top is I've got essentially two scaffoldings crashing together. Each of them is mostly empty space, but they can't fall into each other, and so you can't pass matter through other matter, at least normally. But then you think about that and you're like, well, maybe some of those science fiction ideas could be done, right? I mean, if matter is mostly empty space, maybe someday we'll figure out how two pieces of matter could pass through each other. We don't know how to do that now, but that would be cool, wouldn't it? Any questions?